Okay.
Welcome everyone to this week's QTFMS talk. Today we have the great pleasure of having Edward Witten from Princeton Institute of Advanced Studies. As I'm sure everyone is aware, he's been a pioneer behind many remarkable developments in physics and mathematics. And today he will talk about aspects of black hole thermodynamics. So Edward, thanks a lot for accepting our invitation. We are very excited to have you today, and you can take it away.
Well, thank you for the invitation and the introduction. I'm not sure what happened to my screen share, though.
You can see it right now.
You
There's no
can?
problem. Yeah.
Uh, Somehow, uh, okay. I can't see it, though.
Oh.
I'm going to
Maybe you can try to close and then open again.
yeah, I will. Sorry.
It's okay.
This is okay. Now I can
Yeah,
see my
it's working
screen.
now.
Okay,
Yeah,
fine.
yeah, we can
Okay,
see.
sorry about that delay. Anyway, thanks very much for the invitation. And I'm going to try today to give a basic introduction to black hole thermodynamics, which is one of the areas where there's been exciting progress in the last 10 years or so. There's one thing almost everyone knows about a black hole, even people who aren't physicists. Entering a black hole is a one-way street. What goes in doesn't come out, at least according to Einstein's theory. So this is a computer visualization of a black hole in the foreground with stars in the background. And the black hole appears like a black disk because all the light incident on it is swallowed up and doesn't get to us. Uh, there's, of course, a long story about the deflection of light. So the light going, um, the star background that you see at a distance is highly distorted near the black hole because of the gravitational field of the black hole. Anyway, to state this in the language that's used in thermodynamics, for a black hole to capture something is irreversible. Excuse me, hold on a second. But there's a conflict between such irreversibility and the fact that the laws of nature are actually believed to be completely symmetric between past and future. Of course, we see irreversibility in everyday life. For example, when we break an egg. There's a nursery rhyme about this in English. Humpty Dumpty is seen as an egg sitting on a wall, and if the egg falls and breaks, all the king's horses and all the king's men can't put it back together again. The basic idea of black hole thermodynamics is that the irreversibility in black hole physics is fundamentally not different from the irreversibility in everyday life. How do we understand irreversibility in general? In the 19th century, physicists understood that the basic principle is the second law of thermodynamics. The entropy S counts the logarithm of the number of microscopic states available to a system once you describe its macroscopic state. For example, once you describe variables like the total energy and the total number of particles. An irreversible process is one in which the entropy increases. Differently put, an irreversible process is one in which the number of possible microstates, given the observable macros, given the macroscopic observables, increases. The second law says that S is always a non-decreasing function of the time. A corollary is that any process in which S actually increases is irreversible, or at least prohibitively hard to reverse. If you take an irreversible process, meaning one in which the number of microstates increases, to reverse it, there would be states of the system. Maybe I wrote this. The second law isn't true in every state, only in a generic state. There are some states of the broken egg sitting on the ground, such that it would spontaneously reconstitute and jump up on the wall, but only a very tiny fraction of all states on the broken egg on the ground have that property. The fraction is of order e to the minus the increase in entropy when the egg fell and broke. And delta S is Avogadro's number times a number that's not too small, so e to the minus delta S is fantastically small. So it's prohibitively difficult to manipulate the state of the broken out egg sitting on the ground to put it in one of the special states where it would spontaneously reconstitute and jump up on the wall. By analogy, in black hole thermodynamics, we expect that if a table or chair falls into a black hole, the black hole might spontaneously eject that same table and chair the next day, but that's prohibitively unlikely. Now, black hole thermodynamics started with the work of Jacob Bekenstein in 1972. Inspired by questions, I actually have a question. Can you see my cursor now?
Yeah, I can see.
Okay. Inspired by questions from his advisor, John Wheeler, Bekenstein asked what the second law of thermodynamics means in the presence of a black hole. As I said, the second law says that for an ordinary system, the entropy can only increase. But if we toss a cup of tea into a black hole, the entropy seems to disappear. Bekenstein wanted to generalize the concept of entropy so the second law would hold even in the presence of a black hole. For this, he wanted to assign an entropy to the black hole. Well, he needed a property of a black hole that can only increase. But what property has that? What aspect of the black hole can only increase? It's not true the black hole mass always increases. For example, a rotating black hole can lose mass as its rotation slows down. That's actually believed to be important in understanding the jets that we see coming from black holes at the center of galaxies. But there is a quantity that always increases. Stephen Hawking had just proved the area theorem, which says that the area of the horizon of a black hole can only increase. The horizon is the surface of no return, the boundary of the black disk in this picture. So it was fairly natural for Bekenstein to propose that the entropy should be a multiple of the horizon area. For example, according to Einstein's equations, a spherically symmetric black hole has a horizon radius 2gm. M is the mass and g is Newton's constant. So its horizon area is 4 pi r squared or 16 pi g squared m squared. Since entropy is a pure number, but the area of the black hole horizon has dimensions of length squared, Bekenstein needed to use constants h bar and c to get the units right. I'll set c to 1, but I've included h bar, which appears in the denominator in the formula. And the factor of 1/4 was not clear in Bekenstein's work. Bekenstein just said it was a constant of order 1 there. This factor was determined by Stephen Hawking a few years later in a way that I'll explain. The factor of h bar that appears in the denominator shows that the formula is fundamentally quantum mechanical. In part because h bar is so small in everyday terms, Bekenstein's proposed black hole entropy is very large. For example, a spherically symmetric black hole with the mass of the Sun has an entropy roughly 10 to the 20 times the entropy of the actual Sun. Bekenstein's idea was that the entropy of a black hole captures information lost when the black hole was formed. He interpreted it as the logarithm of the number of ways that the black hole could have formed. And Bekenstein proposed a generalized second law, saying that the generalized entropy can only increase. The generalized entropy was supposed to be the sum of the black hole entropy, A over 4gh bar, and the ordinary entropy of matter and radiation outside the black hole. So the claim was that when something falls into the black hole, S out may go down, but A over 4gh bar increases by more. Bekenstein made a few tests of the generalized second law. Here's one. Well, first of all, Bekenstein assumed that S out was ordinary thermodynamic entropy. So his proposal assumes that the matter and radiation outside of black hole is such that thermodynamics is at least approximately applicable. If you toss something for which, okay, let me stick with that statement. So for example, you could shine black body radiation with temperature T on a black hole. Black body radiation is a good choice because for given energy, its entropy is large compared to other things you can think of. The relation between energy E, entropy S, and temperature T for black body radiation is that E is 3/4 Ts, or S is 4E over 3T. When a black hole of mass m absorbs energy E by absorbing black hole radiation, its mass shifts by m to m plus E, so its entropy 4 pi g m squared changes by 8 pi g me. I'm assuming E is very small compared to m. So both terms in the entropy change are proportional to E, and overall the generalized entropy changes by E times 8 pi gm minus 4 over 3T. So the change in the generalized entropy is positive if T is bigger than this quantity, which is equivalent to saying that the thermal wavelength of the photons, namely 1 over T, should be less than the diameter of the black hole. So the generalized second law worked, assuming that the radiation that the black hole is absorbing has a wavelength less than the size of the hole. But by the same token, the generalized second law does not work in Bekenstein's formulation if the temperature of the radiation is so low that the wavelength is bigger than the size of a hole. And Bekenstein really, if you look at his paper, you'll see he did not have a satisfactory answer in this case. If the black hole is absorbing photons of wavelength larger than the black hole size, which can happen though not very efficiently, it seemed that the generalized second law was violated. In hindsight, this question does not have a satisfactory answer in the framework Bekenstein was assuming, which was that whatever falls behind the black hole horizon stays there forever. In the thermodynamic terms, since Bekenstein assumed the black hole was not radiating, you should assign it a temperature of 0. But thermodynamics says that at equilibrium, the changes in energy E and entropy S of a system are governed by dE equals TdS, or ds equals dE over T. So a system with T equals 0 should have ds equals infinity if dE is non-zero. But Bekenstein wanted to attribute a finite, not infinite entropy to the black hole. In hindsight, we'd say that you can't analyze the absorption of very long wavelength photons by the black hole while ignoring what Hawking discovered a little later, which is that the black hole is strongly emitting such photons. And it turned out that, due to Hawking's work, which I'll come to in a second, that the increase in entropy due to the black hole spontaneous emission is greater than the reduction of entropy in absorbing black body radiation at a very long wavelength. So Bekenstein's problem was resolved, but only when Hawking discovered spontaneous emission by a black hole. Before I go on, I want to say something else about the first law, dE equals TdS. Because with 20/20 hindsight, we can see how what happened next might have been guessed based on the first law. For the energy E of a black hole, we mean mc squared. It's mass, basically, in units where c is 1. And that's independent of h bar. So E has a classical limit. On the other hand, I told you that Bekenstein's proposed formula for S was of order 1 over h bar. So therefore, the temperature you'd infer is proportional to h bar. And that means that the temperature should vanish in the classical limit, in perfect agreement with Einstein's classical theory. In Einstein's theory, h bar was 0, and the black hole was perfectly black with 0 temperature. So in hindsight, because Bekenstein's formula for S is proportional to 1 over h bar, it would have suggested, or it could have suggested, that T is of order h bar and therefore arises as a quantum correction to the classical picture. That's what Hawking discovered, although as far as I know, the discovery was not motivated by this line of thought. Stephen Hawking famously was skeptical of Bekenstein's idea, but he studied the behavior of quantum fields interacting with a black hole, and in the process ended up proving that Bekenstein was right. And he made it in the process his greatest discovery. At the quantum level, a black hole is not really black. It has a temperature proportional to h bar, as the first law plus Bekenstein's formula might have suggested, like I just explained. As preparation for explaining what Hawking did, I want to recall the idea of the Penrose diagram as a convenient way to depict and visualize spacetime. I suspect that the audience varies a lot. Some of you probably know Penrose diagrams at least as well as I do. Others may not be familiar with them. So I'm going to spend a few minutes to just review what a Penrose diagram is. In a Penrose diagram, we usually assume spherical symmetry, and then we depict spacetime showing just two directions, which you can think of as being time running vertically, and a spatial direction running horizontally, which you can think of as the distance from the origin. So for example, on the left, I've drawn a Penrose diagram of Minkowski space. Time runs vertically. The distance from the origin is plotted from left to right. R equals 0, the origin is the vertical left line on the boundary. But future infinity is at the top, past infinity is at the bottom, and spatial infinity is the right corner. In drawing that diagram, the diagram is always drawn so that radially ingoing or outgoing light rays are at a pi/4 angle to the vertical. So for instance, that diagonal purple line that I've drawn, which is meant to be at a pi/4 angle from the vertical, represents an outgoing light ray, a light ray traveling to infinity at the speed of light, but not moving at angles, only moving in separation from the origin, so that the radial distance, dr dt, is increasing at the speed of light. So Penrose drew Penrose diagrams so that ingoing and outgoing radial light rays are at a pi/4 angle from the vertical. And therefore, any causal curve is at an angle from the vertical that's no more than pi/4. So if you want to escape, the fastest escape is at a pi/4 angle from the vertical, or you can go slower. But you can't travel in this picture at an angle bigger than pi/4 from the vertical. Penrose had one more crucial insight which is built into this picture, which is that since what we really care about is depicting causal relations, we want to preserve the angle, notion of a pi/4 angle from the vertical, we can make a conformal mapping to move infinity to a finite distance. And that's been done in drawing the picture. So a conformal mapping is made so that future infinity is at a finite distance, past infinity is at a finite point, and spatial infinity is at a finite point. And future and past null infinity are also, they're these diagonal lines at the edge of the diagram. They're all at finite distances. So what Penrose did with the Penrose diagram was make it easy to visualize causal relations with the benefit of a conformal mapping that moves everything to a finite distance so that it's easy to visualize. So this is the Penrose diagram of Minkowski space. Now on the next slide, I'm going to draw the similar Penrose diagram of a black hole. So here's the Penrose diagram of a black hole. And future infinity is still labeled I plus. It's this point here. But the fundamental difference from Minkowski space is that an observer at I plus can't see the whole spacetime. From I plus here, you can see the whole spacetime because a signal from anywhere can reach I plus while going at an angle less than pi/4 from the vertical. But here, because the signal can only travel at an angle at most pi/4 from the vertical, an observer in the far future at I plus can see only the part of the spacetime that's to the past of this diagonal line labeled the horizon. The diagonal line itself is at a pi/4 angle from the vertical. So it reflects the boundary of a signal that's going to reach either future null infinity or just future infinity at I plus, traveling at an angle no more than pi/4 from the vertical, has to start from on or below the horizon. From beyond the horizon, at no more than a pi/4 angle from the vertical, you'll inevitably end up at this wiggly line, which depicts the singularity at the center of the black hole. In this picture, the green region is the part of the world volume that's filled by the star that lived its life and then collapsed to a black hole. The star in this picture originated its life at I minus. That assumes the star formed from massive matter rather than massless radiation. The fact that the star appears to emanate from a point is an artifact of Penrose's conformal mapping in drawing the diagram. So this is a thumbnail picture of the Penrose diagram of a spherically symmetric black hole, a so-called Schwarzschild black hole, formed from the spherically symmetric collapse of a star. Now, a key fact in physics is that observations at one time can be traced back to initial data at an earlier time. And in particular, observations that we make at future infinity or future null infinity can be traced back to initial data at any earlier time of our choice. In general relativity, earlier time means on a space-like hypersurface. It's convenient to pick an initial time hypersurface that crosses the horizon to the future of the collapsing star. So in other words, I've taken the surface S that intersects the world volume of the star only behind the horizon. So any signal we can receive at infinity will come from S, but from the portion of S outside the horizon. Only the portion of the initial surface S outside the horizon is visible to the distant observer. And then I've drawn in this diagram these diagonal purple lines that represent signals traveling from the surface S to infinity at the speed of light. And these signals pile up near the horizon because of the gravitational redshift. So signals that, let's say, appear 1 second apart in Schwarzschild time, measured at spatial infinity, well, they all originate from outside the horizon, so they have to originate from closer and closer to the horizon as time goes on. So these outgoing purple lines are depicted as piling up near the horizon because of the redshift. Now we ask, what will the observer see? Well, part of Hawking's insight was that although the full details of exactly what an outside observer sees depends on the precise quantum state of the collapsing star, if you ask what the observer will see in the far future after transients die down, there's a universal answer. The key point about this picture is that a signal that's received very late by the distant observer, which means very close to this point I plus, originated from very close to the horizon. So late time measurements of an outside horizon observer can be interpreted as measurements of the state of the quantum fields at short distances near the horizon. But every state is equivalent to the vacuum at short distances. So the late time observations of the observer probe the vacuum state near the horizon at short distances. That's why Hawking got a universal answer, regardless of exactly how the black hole formed. So to be a little more quantitative, I'm going to let U be a coordinate function that vanishes on the horizon on some particular Cauchy slice, which will be this slice S, and it's positive outside. It doesn't matter precisely how U is defined. So here I've drawn, again, the part of the picture that's important. The part of the picture that's important is the horizon, first of all. Then there's the initial value surface, shown in red. All that we care about is that it's to the future of the collapsing star. The star has disappeared up here, and now I've drawn an initial value surface that stretches outward from the horizon. It also stretches behind the horizon, but we can't see that part. And we're going to measure at time t what's coming out of the black hole, and whatever comes out got out at the speed of light from very close to the horizon. So we want to know the relationship between t, the time at which the signal gets out, and u, the distance from the horizon at which it started. So t will be the time at which a signal is detected by an observer at infinity. And the relation between u and t involves a logarithm. T is 4gm times the log of 1 over u, plus a constant, plus a correction of order u and higher orders. You find this formula from solving the geodesic equation for an outgoing null geodesic, or in other words, from Einstein's description of the behavior of light in a gravitational field. So the constant C0 depends on how you define u. If you rescale u, that will shift C0 by a constant. You see, rescaling u will add a constant to the logarithm, which will shift C0.
चेक कर यार एडवर्ड विटन लाइव है कौन
I can't hear you, sorry. Say that again.
I think there's a problem with the sound, so we can keep going.
There's a problem with what?
I think it was a mistake. There's no question.
Okay. Uh,
By the way, can I ask a question? So
if there's a
what you're saying
question,
is that
feel free to ask. What's that?
So according to what you're saying, the observer does not depend on how we find it, right?
Sorry, I didn't quite hear that. I couldn't hear that, sorry. We can
just continue. Sorry about that.
Okay, but I am
Just
happy
continue,
to
sorry.
take questions. Okay. Okay.
There
Unfortunately,
was some background noise. Sorry about that.
okay, but okay. Okay, I'm not sure if you can see my slides, but I've lost them again. Are you seeing the slides?
Yeah.
Okay.
Yeah, it's okay.
Okay. Okay. Okay, I'm back to being able to see. I am happy to stop for questions, though, if there are questions.
Actually, can I ask it now? Because I'm in a quiet place.
Yes.
If I understand correctly, what you mean, the observer does not depend on how we define U parameter.
This relation doesn't depend on you in the following sense. If I rescale you, I'll add a constant to C0. But if I reparameterize you by, for example, adding U squared and so on, that'll make a correction of order U, which will be completely insignificant in a moment. So
I
the
see.
only
So does that, sorry. Does that mean that the observer is not local?
the observer is way outside the black hole. The observer is us, maybe a light year away from the black hole. And T is time measured by us. I didn't define it precisely, but the region far from the black hole is asymptotically flat. The observer is basically in Minkowski space. And you can think of T as being ordinary Minkowski space time.
Okay.
U is the distance from the horizon at which the signal is emitted, and T is the time at which the signal is detected.
Okay.
And something which you all know is that if U is negative, the observer will never get the signal. But the way that works is that the smaller U is, the bigger is the T at which the signal is detected. As U goes to 0, T goes to infinity. And if U is negative, you never see the signal. So as U goes to 0, you have to wait longer and longer. But as U goes to 0, although T goes to infinity, it only goes to infinity logarithmically, which might not seem so dramatic. It seems more dramatic if we solve for U in terms of T. If I write the same formula in terms of U, it takes the form that U is a constant times e to the minus t over 4gm. And this is dramatic because it says that as t goes on, U becomes exponentially small. So signals that a late-time observer sees can be considered to have originated from exponentially close to the horizon. A basic fact about quantum theory is that at sufficiently short distances, any state of the universe looks the same and is equivalent to the vacuum. That's actually why Hawking got a universal answer, independent of how the black hole formed. A late-time measurement is simply probing the vacuum at short distances.
Can I ask something?
Yes, go ahead.
On the previous slide, when you solve the equation and you, no, the next one. When you solve for U, you basically find the particular Cauchy slice, as far as I understand.
Well, I took a particular definition of U, but the precise definition doesn't matter. You can also see it here. If, first of all, U is going to be exponentially small because of this formula. So a correction of order U squared will be completely irrelevant. But what about a correction of order U? If I replaced U by 2U, that would be like shifting T by a constant. So if the observer, the constant would be of order the time for light to cross the black hole, by the way. So if the observer is going to make a late time measurement, well, we didn't say exactly how the observer set his watch anyway. So what exactly did T mean? You could always add a constant to T.
Okay.
So nothing about this formula depends in an essential way on either U or T. What the formula shows is that as T goes on, U becomes exponentially small. There is a constant in the relation that depends on how you set your watch and how you define U. But the important statement is that as T goes on, U becomes exponentially small. And that means that late time measurements are observations of quantum fields at exponentially small distances near the horizon. And since every state looks like the vacuum at short distances, that's why Hawking got a universal answer independent of how the black hole formed. A late time measurement probes the vacuum at short distances. Now, what is meant by late time, though? Late time just means the time is long compared to 4 GM. So, for example, for a solar mass black hole, 4 GM is something like tens of microseconds. I don't remember the exact amount. So, after 1 second, this exponent is something like e to the minus 100. So, one second after a solar mass black hole formed, whatever you observe 1 second after the formation of the black hole involves measuring the quantum fields incredibly close to the horizon, much closer than we're able to get with normal experiments. So the LHC works very hard and makes measurements roughly down to 10 to the minus 17 centimeters. But a measurement of what comes out of the black hole 1 second after it formed, this is for a black hole with the mass of the sun, is seeing down to much smaller distances than that. The catch is that at the LHC, whatever they see at 10 to the minus 17 centimeters, they can really see. Whereas at the black hole, the signal originated at exponentially small distances, but then it undergoes a huge exponential redshift, which hides an awful lot from us. So what we're able to finally observe, as we'll see in a moment, is limited.
Sorry, can I ask something?
Yes, go ahead.
So what do you mean by vacuum when you're dealing with quantum field theories in curved spacetime? Like,
Well, curved space-time at short distances, you can think of gravity as just another quantum field. At short distances, the gravitational field and everything else is, for all practical purposes, in the ground state. A sufficiently small piece just looks like a piece of Minkowski space, and the quantum state looks like the vacuum.
so like I need a choice of time for which, with respect to which I can define the vacuum, right? So the time here is the t.
No, you don't need to make a choice. Just the vacuum in Minkowski space is Lorentz invariant. It doesn't depend on the choice of frame. So the statement I made didn't only depended upon the fact. Yeah, the statement I made didn't depend on such a choice. Are there any other questions? So what does,
Hello, I have a question.
yes,
The solution that was as far as I know that was used here is the Schwarzschild solution, correct?
yes.
Can we do so using the Vaidya solution? Can we like get the same answer or like intuition of what's happening?
The details of the Schwarzschild solution are ultimately unimportant, but you have to understand how it works before you can understand that.
Oh, okay. Yeah.
So what is the observer at infinity going to measure? The observer at infinity will measure the radiation by measuring a quantum field that I'll call psi of t. In the real world, you would most probably measure the electromagnetic field, because most of what would come out of the black hole, or at least most of what would come out that you can easily measure, would be photons. But I'll consider a simpler model that I'll specify in a second. Now, when you measure the quantum field, what do you measure? The most basic thing you measure is what's called a two-point function, the correlation between the values of psi of t at two different times t and t prime. So, assuming that that the signal you're observing is time independent, the two-point function only depends on the difference t minus t prime. And when you measure the spectrum of radiation coming out of the black hole, what you're doing is measuring the Fourier transform of the two-point function. Of course, if it's visible light and you split it with a prism, you measure the spectrum directly without measuring in the time domain and taking a Fourier transform. So it might be easier to measure the spectrum in some other way than this mathematical algorithm. But mathematically, what the spectrum is the Fourier transform of the two-point function. Now, near the horizon, a typical quantum field has a power law singularity. So technically, I'm going to take a model where the quantum field, I'll consider an effective 1 plus 1 dimensional model. Okay, I'm going to look at S-wave modes coming out of the black hole. So S-wave modes depend on time and also the distance from the black hole. And so suppressing the radial coordinates, we can describe a particular partial wave coming out of the black hole by a 1 plus 1 dimensional effective field theory. And in that effective field theory, I'm going to assume that psi is a fermion of spin half, a massless fermion of spin half. In that case, the two-point function has a power law singularity 1 over u minus u prime. And this numerator is just my way to remind myself that under a change of coordinates, psi transforms with spin 1/2. If the numerator confuses you, ignore it. The important thing is that the two-point function has a power law short distance singularity. In general, typically quantum fields have power law singularities at short distances. And for simplicity, I'm taking a model where the power is 1.
Just out of curiosity, can this quantum field be the gravity itself?
It could, yes. And the only trouble is that then you would have to use tensor spherical harmonics. So technically, you have to work much harder if you want to study observations of outgoing gravitons. For photons, you have to use vector spherical harmonics, right? So technically, the computation is more complicated for gravity, but the analysis is ultimately the same because what everything comes from is a power law singularity at short distances, and all quantum fields, including the gravitational perturbations, have such power law singularities. For gravity, the power would be, or for photons, for bosons in general, the power is 2, whereas here I'm assuming 1 for fermions. So we have the formula for what it would look like if you were living near the horizon of the black hole and measuring there. So ignoring the numerator, if you were able to measure near the horizon of the black hole, where u and u prime are both exponentially small and therefore they're exponentially close to each other, you'd see a strong correlation proportional to 1 over u minus u prime, and its Fourier transform is what you would measure by probing the vacuum. All we have to do to see what the distant observer measures is to change variables from u to t using this formula. And when we do that, this formula turns into this one. All I did was to take a power law singularity with the power of 1 and change variables using the relation between the distance from the horizon and the time measured at infinity. We got this. And you'll notice that this answer is anti-periodic in imaginary time. It's odd under t going to t plus 8 pi gm times I being the square root of minus 1. Well, it's anti-periodic because I assumed fermions with a singularity with the power of 1. For bosons, we would have gotten something periodic in imaginary time with the same period. Anti-periodicity for fermions or periodicity for bosons in imaginary time corresponds to a thermal correlation function with a temperature which is the inverse of the period. So the temperature is 1 over 8 pi gm, nowadays called the Hawking temperature, T sub h. And if I included Planck's constant, it would be h bar over 8 pi gm. Maybe I've written that on the next page. So this is how Hawking learned that a black hole, after transients that depend on how it was created die down, radiates thermally at a temperature 1 over 8 pi gm. We can now also confirm the value of the entropy. Using the relation dE equals TdS, for the black hole E is m, and we learned that T is 1 over 8 pi gm, so ds is 8 pi gm dm, and assuming that s is 0 and m is 0, we integrate to learn that s is 4 pi gm squared. But the area of a spherically symmetric black hole we computed at the beginning to be 16 pi g squared m squared So the entropy is A over 4G. So that's how Hawking confirmed and sharpened Bekenstein's proposal. Now, I should tell you that I've cheated slightly in this derivation to make it simple. I ignored the interaction of the outgoing radiation with the gravitational field of the black hole. I believe the derivation I've given is actually completely correct if the radiation you're observing is an electrically charged massless fermion and the black hole is magnetically charged. But in a more realistic case in the real world, the interaction of the outgoing radiation with the gravitational field of the black hole is important and makes a longer derivation that leads to essentially the same answer, except for what's called a gray body factor. If you want to, well, there are many places where you can read a more careful derivation that discusses the gray body factors. One of them is my lecture notes, which have, I think, the same title as the lecture. Anyway, they're on the archive as of last December or so. There are lots of other places you can read it, but if you look there, you'll find my version of the explanation. Anyway, even though I cut some corners so we didn't have to discuss gray body factors, I think I've explained the essence of the Hawking effect. I didn't include the h-bar in here, but you see, as I told you earlier, this formula implies that T should be proportional to h-bar, and there is an h-bar for dimensional reasons. If we restore h-bar and C in this formula, there is an h-bar in the numerator. So that's why there's no conflict with Einstein's classical theory in the limit h-bar goes to 0. This is a quantum correction to Einstein's picture. Because the black hole emits thermal radiation, it loses energy and evaporates, according to Hawking. But the timescale is very long. For instance, a solar mass black hole in vacuum takes 10 to the 67 years to evaporate, compared to the age of the universe, which is more like 10 to the 10 years. So we don't expect to observe black hole evaporation unless we're very lucky in some way. For example, if very tiny black holes were created in the Big Bang, for which we currently have no evidence. But we do observe in cosmology something that's believed to be very similar to Hawking radiation from a black hole, namely inhomogeneities in the early universe that are believed to have been the seeds to formation of galaxies. Unfortunately, to explain that part of the story would take us in a different direction today. And Hawking's calculation is of great conceptual interest. Indeed, it poses a puzzle that's driven a lot of research in the half-century since Hawking's work was published. In Hawking's calculation, the radiation that comes out of a black hole appears to be exactly thermal, with no correlation between the different particles that come out of the black hole at different times, except what follows from conservation of energy and the temperature of the black hole. If that's strictly true, it would mean that black hole evaporation cannot be described by fundamental microscopic equations that are invariant under reversing the flow of time. To see this, consider a process in which a star collapses to a black hole which then evaporates. If physics is really described by microscopic laws that are time reversal invariant, then from the decay products of the black hole, it must be possible in principle to reconstruct the detailed quantum state of all the atoms in the star before it collapsed to make a black hole. You must be able in principle to run the movie backwards, describe the state of the universe in which the outgoing decay products are reflected backwards and recombine to make a black hole that then explodes to make the original star. Therefore, the state of the outgoing particles cannot just be thermal. There must be subtle correlations which contain the information needed to reconstruct the detailed microstate of the original star. But how that happens, well, to understand that better, if you like, is the central mystery of the subject. A clue is simply that black hole entropy is so big. For instance, as I remarked, the entropy of a black hole with the mass of the Sun is much greater than the entropy of the actual Sun. Many researchers have thought that somehow the entropy A over 4G means that the black hole can be described by some sort of degrees of freedom that live at its surface, with roughly 1 bit or qubit for every 4G of area. For example, in a famous article, John Wheeler illustrated that idea with this picture, where he visualized the black hole horizon as being made out of little cells of area roughly 4G, each of them being labeled by a 0 or 1, which he thought of as the outcome of some kind of binary measurement. As I said, the article was published in 1992. I suspect that Wheeler had been Bekenstein's advisor. Bekenstein's original work was 20 years earlier. I suspect that Wheeler had been drawing this picture for a long time, although as far as I know, he first published it in this article in 1992. But for now, to really understand the deeper lesson of black hole entropy is beyond our understanding. I'm going to use the remaining time to discuss the following question. What is a white hole? Naively, a white hole is the time reversal of a black hole. So Einstein's equations are invariant under time reversal. So just by applying time reversal to the black hole solution, we got what's been called a white hole solution. So on the left, the Penrose diagram of a star collapsing to a black hole. There's a singularity in the future seen by the wiggly line. And I hope the picture is big enough you can see it. But the far future is this point I plus. From I plus, you can see what's to your past, but you can't see what's beyond the future horizon, this diagonal black line. Time reversing the picture, we have what's called a white hole singularity in the past. The white hole singularity emitted a star, which then escaped into the wide world. And the outside observer can see everything. You can see the past singularity. It's therefore called a naked singularity. But you can't influence what's beyond the past horizon. So the diagonal black line here is now a past horizon. If you're living in the outside world, you can see what comes out from the past of the past horizon, but you can't influence it. You can't send a signal back there. So the white hole solution, although it might seem strange, is simply the time reversal of the black hole solution and makes perfect sense as a classical solution of Einstein's equations. So to summarize, in A, we see the collapse of a star to make a black hole. In B, a white hole spontaneously converts into a star. Classically, anything can fall into a black hole, but nothing can come out. Time reversing that statement, we learned that a white hole has the property that anything can come out, but nothing can fall in. A white hole is a little like a mini Big Bang from which matter, or in the example I've drawn, a star, emerges in an unpredictable way. White holes may sound even stranger than black holes, but we don't see anything that we interpret as a white hole. And you could ask, why not? Well, from the point of view of black hole thermodynamics, the formation of a black hole is a process in which the entropy increases. So the time reverse process in which a white hole spontaneously converts into a star is a process in which the entropy becomes smaller, violating the second law. As I explained at the beginning, the laws of nature have solutions that describe histories in which the entropy becomes smaller, but these solutions require fine-tuned initial data and are prohibitively unlikely in practice. So, as an example, the entropy increases when a pen, unstably balanced on its tip, falls down, dissipating its kinetic energy into heat. So in my office, I was not able to balance that pen perfectly on its tip, but I balanced it well enough that I was able to snap this photograph before it fell down. And as you can imagine, a little bit later, it did fall down, increasing the entropy. I wasn't able to create the time reverse solution in which the pen spontaneously rose up off the table and balanced in unstable equilibrium at the top. So the laws of nature do have time reverse solutions in which the pen spontaneously absorbs energy from the air in the table and rises up, reaching an unstable position in which it's balanced on its tip. But we never see such behavior in practice because the initial conditions that would lead to such behavior are prohibitively rare and fine-tuned. So of course, this is what I said at the beginning, except at the beginning of the talk, I gave the example of breaking an egg rather than the falling pen. But having reminded ourselves of this lesson, what would we say about the white hole? Well, black hole thermodynamics suggests that the white hole spacetime is similarly fine-tuned, and an infinitesimal perturbation should prevent white hole behavior and the decrease of entropy. In fact, the mechanism by which this happens was first described by Eardley a little over 50 years ago, around the dawn of black hole thermodynamics, but not motivated by black hole thermodynamics, as far as I can see from his paper. The mechanism is essentially the time reversal of the mechanism by which Hawking discovered black hole evaporation. I think the two papers by Hawking and Eardley were published at practically the same time. And I don't know who it was who first recognized that Eardley was discovering the time reversal of what Hawking had discovered. I would like to say I was not the one who made this connection, but I don't know who did. And I'd be happy to hear the reference if anybody can suggest who first made this connection.
May I ask a question at this point, please?
Yes, go ahead.
So regarding the thermality of Hawking's radiation and that the contents of the black hole are forever lost or not, I don't see why having a black hole is so special. Let's conduct a very short thought experiment where I write a letter and put it into an oven, and I measure all the quantum fields and their correlators, let's say
Yes.
2-point
Yes.
correlators. Presumably it's thermal, but presumably also if I measure all endpoint correlators, I should be able to reconstruct the contents of the letter. So how is the oven different from the black hole if you consider all endpoint correlators of quantum fields? And does Hawking radiation tell us anything about the endpoint correlators?
Well, first of all, as I said at the beginning, the idea of black hole thermodynamics is that black holes are not fundamentally different from other processes. So the answer we expect, the point you've made has been made by many, many people for decades, actually. And the answer we expect is precisely what you've said. But in the case of the oven, we have a framework of the Schrodinger equation, or at a more fundamental level, the standard model of particle physics that's adequate to describe the process in a unitary fashion, exhibiting that quantum information is preserved. In the case of the black hole, we fundamentally don't have a framework that enables us to describe the evaporation and disappearance of the black hole, exhibiting unitarity in the process.
Thank you.
I'd like to ask, though, that questions should be focused on what I'm explaining at a given point. You'll all have time at the end to ask questions on any previous part of the talk. So as I was saying, black hole thermodynamics suggests that white hole behavior is fine-tuned and non-generic, and therefore that we won't observe it in practice. And the mechanism by which this happens is essentially the time reversal of the mechanism by which Hawking discovered black hole evaporation. In fact, when the last questioner spoke up, I was hoping maybe you would tell me what I just asked, which was what's the original reference to who made the connection between Eardley and Hawking, since it was certainly not me. Now, remember, so before explaining since what Eardley said was the time reversal of what Hawking said, let's just remember what Hawking said. Hawking's reasoning depended on an enormous exponentially big redshift that an outgoing particle experiences as it propagates from the region near the black hole horizon to the region at infinity where an outside observer might detect it. So remember, something I didn't stress was that the Hawking temperature is such that a typical photon at that wavelength, at that temperature, has a wavelength which is the size of the black hole. So the photons that come out of the black hole are very low energy photons. Their energy, for a solar mass black hole, these would be photons with a wavelength of something like 1/10 kilometers, and correspondingly, a frequency of maybe 100 kilohertz or something, but a very low frequency compared to the frequency of light we usually interact with. So the radiation comes out with a very long wavelength, but it originated at the horizon, near the horizon, at a very short wavelength. And then it was exponentially redshifted. So it comes down to us as a low energy signal, though it originates at high energies. Both parts of that are important. The fact that the outgoing photons are low energy is why the black hole lives so long. And if you like, it's related to the fact that the temperature is proportional to h bar. But the fact that the signal originates at short distances or high energies is the reason that the answer is universal. Anyway, this exponential redshift is the key to the Hawking process. So what we could call the Erdley process will depend on an exponential blue shift that's the time reversal of the exponential redshift. So in the Hawking effect, the particle eventually detected by the outside observer with moderate or very small energy had an extremely large energy as it was leaving the black hole horizon. Let's consider the time reversal of this. The time reversal is that an observer far from the white hole sends in a particle of very low energy, for example, a few low energy photons. Or we didn't need the observer, this could have been just a quantum fluctuation. But anyway, there's some kind of signal that comes in from the far past at very low energies. And I've actually drawn it, this diagonal purple line labeled gamma represents an inflowing signal that originates at very low energy just outside the past horizon, which is the diagonal black line labeled H. It originates in the far past at very, very low energies, comparable to the temperature, well, comparable to the Hawking temperature, but it's exponentially blue shifted. And by the time this incoming particle interacts with the star, it has an astronomically large energy, comparable to the rest mass of the star or more. So a tiny perturbation of the white hole spacetime leads to a collision of the star with a perturbation of astronomically large energy. The collision of these ultra-high energy photons with the star that was escaping from the white hole drastically changes the spacetime geometry. Though we actually don't know the laws of nature at the ultra-high energies that can be reached here, one would presume that a black hole forms, preventing the violation of the second law of thermodynamics that the idealized white hole solution exhibits. Thus, the white hole solution is unstable, like a solution in which the pen spontaneously rises up off the table, or in which Humpty Dumpty is spontaneously reconstituted and rises up on the wall. A tiny perturbation acting in the past can completely change the course of events and prevent the violation of the second law that the white hole solution would describe. All this is as suggested by black hole thermodynamics. To summarize then, today I've tried to give you a taste of one of the most fascinating, unfinished subjects in theoretical physics, the thermodynamics of black holes, which is a truly mysterious relationship between relativity, quantum mechanics, and thermodynamics. Hopefully, some of you will go into this subject more deeply and play a role in unraveling some of the mysteries. Thank you very much.
Thank you, Edward, for this great talk. Now we can take some questions from the audience. Maybe, okay.
Yeah. How does this relate to the thread in physics like the ADS-CFT? Like I just recently read that the chaos bound on the quantum systems is like connected to the surface area of the black hole, which is also connected to the thermodynamics, the entropy of the black hole.
Well, I'd say the main relation to ADS-CFT is that ADS-CFT gives us a framework in which we can pose some of the questions more sharply, because we believe that in the boundary theory, we do have a non-perturbative definition of something, of standard quantum. Well, first of all, the black hole in ADS-CFT, the black hole is definitely dual to an ordinary quantum system because the black hole is simply a microstate of the black hole is simply a high energy state of the boundary CFT. So ADS-CFT gives us a sharper version of the puzzles about black hole thermodynamics, and has given us a tool in which there's been some insight. A little bit hard to summarize in this lecture, but the question involves a very good direction to go into if you want to understand the subject more deeply. You'll see a little bit of that, but only a little bit if you look at my lecture notes. There's been much more discovered in the last 10 or 15 years. Any other questions?
I have a question, if you can hear me.
Yes.
In terms of fluid models of black holes, we can define a black hole itself in terms of a van der Waals fluid. So then we can also define thermodynamically a volume for a black hole. How do you think about how it enters to this picture so that we can discuss about the volume and the entropy of the black hole or the white hole in this sense?
There certainly have been discussions of volume, of the black hole volume. I think it's been claimed that if you could think of the cosmological constant as a variable parameter, then the volume would be in some sense conjugate. I'm not sure that those arguments have gotten very far, but it's a direction you could look at and try to pursue further.
Thank you.
Oh, can I ask a question?
Can I you mentioned like earlier that in ideal white holes cannot exist. Is there like any way to be able to force it to like exist, the existence of a white hole?
Well, I didn't, sorry. I explained the sense in which we think white holes shouldn't exist. White holes are possible as quantum histories. They're just extremely unlikely and fine-tuned. A white hole history is like the case of the egg on the ground, spontaneously reconstituting and jumping up on the wall. It violates the second law, but the second law is only true for all practical purposes. The laws of nature allow solutions where the second law would be violated.
Oh, okay, thank you.
Oh, can I ask a question? Yeah. I was wondering, like, more from the conceptual side, whether like we have an infinite universe, and then like even if it's unlikely to have a white hole, then at some point there might be a white hole, like in the very far-fetched case scenario. Then in this case, would we be able to measure this white hole like in some way because it produces a photon that for some reason it gets like very high energetic? Would that be like a measurement we could do?
Well, I feel the question's a little bit like asking whether in my office I could measure what happens when the pen spontaneously lifts up off the table and bounces on its tip. So, um, good luck trying to measure a violation of the second law.
Yeah, I feel like the reason I asked the question is because you mentioned that it gets to high energies that we don't even understand the physics. So I guess would that even be measurable? Because it gets to like Planck scale energies type of thing.
Well, you see, we can't describe the details of the reaction, but most likely it's surrounded by a black hole horizon. So uh, I think the most likely outcome is that the white hole is really a black hole because I drew it as if there was one particle coming in, but in reality, there were quantum fluctuations, quantum mechanically. Let's discuss the case of the pen sitting in unstable equilibrium on its tip. In Newton's laws, we'd say that that solution exists, but the probability to see it is 0. But we actually would not say that quantum mechanically. Because quantum mechanically, there always are fluctuations in the position, and therefore the pen will always fall down. Put it differently, since quantum mechanics only makes statements about probabilities anyway, in something that has probability 0, you would just say quantum mechanically it doesn't happen. The classical statement, what could happen but the probability is 0, doesn't make any sense quantum mechanically. So I think because quantum fluctuations would have emerged even in the arbitrarily far past, the white hole situation, quantum mechanically, is probably rigorously impossible.
Thank you.
Can I ask a question about white
Yeah.
holes again? So let's say we try to construct a solution of Einstein's equations that has like a one white hole and a black hole far apart, and then we slowly try to close them together, bring them together. What does the equations tell us about the dynamics of these? Like, how do they interact according to Einstein's GR?
Well, before trying to do that, you might ask what happens when two black holes are nearby. So
Okay.
it took decades of very hard work before people were able to do computer simulations. Einstein's equations are complicated nonlinear equations. The thing about your question, though, is that because the white hole solution is unstable, you might have trouble making sense out of it. As I told you, any tiny perturbation drastically changes the white hole spacetime. And a nearby black hole is definitely a perturbation.
I see.
So your
Okay.
question at least has the complications of two black holes, but okay.
So
However,
we cannot try to understand like a particle anti-particle collision,
well,
something
white
like
hole,
that.
you should not think of white hole similar to a black
Yeah,
hole.
okay.
If that's what you thought, you got the wrong message from the lecture.
Okay.
Um, a white hole is like the pen is sitting in an unstable equilibrium. It's not true that the pen in unstable equilibrium is the antiparticle of the pen sitting on the table. It's just an
Yeah,
unstable.
but it's like somehow opposite in terms of time reversal symmetry. So that's why I was thinking like what happens when they are close together. I mean, it
Yes,
was a rough picture, but yeah, it's not a
you,
correct way to look at it.
yeah, it's okay. It's like claiming that when you boil water, um, the antiparticle of that is a state in which the
Mhm.
water cools down and the gas that you burn to boil the water flows back into the stove.
Yeah, I see. Yeah, that makes
That's
sense.
not, that the relation between those two is not similar to the relation between a particle and an
Mhm.
antiparticle.
Yeah, okay.
The purpose of the point of the last part of my talk was rather to make you realize that a white hole is, well, first of all, black hole thermodynamics would predict that a white hole is unstable, and then we investigated and found in what sense that's true.
Okay.
Hi, Sir Witten. I have like a final question. Can you hear me?
Yes.
Okay. Yeah, so like recently the Hawking's area theorem was like uh, there was an evidence for the Hawking's area theorem to through gravitational wave, right? But like how do you think would be able to prove the Hawking radiation? Does it can we like do so through the analog uh Hawking radiations, for example, in condensed matter system, or like is there any way to detect it uh,
Well, as I
astrophysically?
as I said during my lecture, unless we're very lucky, we won't see Hawking radiation from black holes astrophysically, but we have seen something that's believed to be very similar, which are the almost Gaussian fluctuations in the early universe that we believed are the seeds of galaxies, of galaxy formation. If I were giving a lecture like this one, but on cosmology rather than on black hole thermodynamics, I would have explained, I would have tried to explain the theory of those early universe fluctuations. And it's really, as you would then see, quite similar to the theory of Hawking radiation. So we've already observed in cosmology something that's much more relevant, in my opinion, than any condensed matter analog.
Oh, thank you.
If you have time, there are two questions in the chat that I can read to you.
Okay, go ahead.
The first one is what is the key difficulty in trying to explain the evaporation of the black holes while preserving quantum information?
Well, the key difficulty is that we don't have a non-perturbative version of the bulk theory. So the only, first of all, you need to go beyond perturbation theory to answer that. So you need a non-perturbative description of the theory. And the only non-perturbative description of the theory that we know is in ADS-CFT duality. And what we learn from it is that, yes, the process is unitary, but we don't get any insight into how that happens from a bulk point of view. What's the other question?
Okay, from a quantum perspective, why does entropy scale with the area of a system's boundary rather than with its volume?
Okay. The question is, why is a black hole entropy proportional to its area instead of its volume?
Yes.
Well, one question you can ask is, well, I'm torn between a few possible answers. And I'm going to throw off a few possible answers without careful thought about which is the best answer. So one answer is that at some level it's a mystery why the black hole entropy is proportional to its area. I drew Wheeler's picture with the horizon area divided into little cells, but nobody has fully justified that picture or really justified it. So answering the question is really a challenge to the audience. So as I said at the end of my talk, hopefully some of you will go more deeply into the subject and help in answering that question. A second possible answer is that we can see the surface area of the horizon, but we can't see what's behind the horizon. So it's not totally clear that the volume is well defined, or even it's not even totally clear which volume you'd want to measure. Right? You could consider all kinds of surfaces behind the horizon. But the horizon area is actually a well-defined thing. You can measure it from outside.
Could I ask
There's
a
a
question?
A third answer I can think of is that there's a Hawking area theorem, which is the classical limit of the second law from Bekenstein's point of view. And there's no Hawking volume theorem.
Please, Professor, could I ask a question?
Go ahead.
It's a general question. What are the most important pieces of advice you give to your students to become successful physicists?
Well, the only general advice is to learn everything you can when you're young and take advantage of opportunities.
Okay, thank you very much.
Sure.
If you have time to question in this chat.
If there are more questions, sure, no problem. What other question is there?
Okay. Should I read it or can you see? I can read it to you.
What do I think of lab-grown black holes? Well, unfortunately, we can't make lab-grown black holes. Our technology is nowhere near being able to make a black hole in the lab. Perhaps you're thinking of condensed matter analogs, but I don't think condensed matter analogs capture the nature of the problem. As for lab-grown black holes, well, what's the closest we do come? There's the inertial fusion experiment in the US, where laser beams, you have a pellet of matter and you compress it with laser beams, and you heat it up to temperatures at which fusion occurs. But you can't come anywhere near. You're many orders of magnitude away from being able to create a black hole in the lab. If you could create a black hole in the lab, I can imagine you could learn a lot.
May I ask a question, please?
There was a question in the chat that I wasn't asked. Are we expecting
Yeah,
to have
should I read? Okay.
No, I'm reading. The question is, quantum mechanically, do we have black hole singularities and horizons? Well, we think the black hole eventually evaporates, so there's not a horizon that lasts forever. But in the limit of a massive black hole, the horizon is extremely long-lived. So that's what the horizon means, we think. As for singularities, the quantum meaning of the classical singularity is obscure. So I won't be able to answer that question. But I don't say. One thing you might want to bear in mind is that in quantum gravity, we don't expect to have space-time because the metric at different times doesn't commute with itself. So a maximal set of commuting observables is the spatial geometry, but not the space-time geometry. So since in quantum gravity we don't have space-times in a precise sense, we're also not going to have future singularities in a precise sense. But I don't offer that as the full answer to your question, just as a fact you should bear in mind.
Can I ask something?
Go ahead.
In the swampland program, there is a conjecture stating that there are no global symmetries conjecture, which is motivated by the black hole operation scenarios. And in that sense, does this conjecture say something about the black hole information? Is there a connection between these two?
Well, it doesn't help very much. It tells us that black holes interact with gauge conserved charges, but not with global conserved charges. There are a variety of arguments, of which you've cited one, that go in that direction. Actually, if you want to see my attempt to describe those arguments, I have an article called Symmetry and Emergence, and where I gave a rundown of the arguments. Nothing was original. I just reviewed all the arguments, though, concerning global symmetries. Any other questions?
May I ask one?
Go for it.
I was wondering if these microstates have anything to do with brain configurations.
Well, I mean, a partial answer to that question. You see, any answer to that question involves much more technicality than I've tried to get into in this lecture. But for supersymmetric black holes in a certain situation, as shown by originally Vafa and Strominger more than 30 years ago, or about 30 years ago, you can count them by counting brain configurations in a certain situation. And people have kept improving that ever since. So supersymmetric black holes can at least be counted in terms of brains.
Thank you.
That type of thing hasn't shed much light on the type of puzzles. You see, Hawking radiation, black hole evaporation is for non-supersymmetric black holes. And the puzzles that raises haven't been helped very much yet by the interpretation in terms of brains. I was asked if black hole thermodynamics applies to a cosmological horizon. Yes, basically, according to Gibbons and Hawking. Would a collapsing universe have a white hole type horizon? Well, an example of a collapsing universe is the interior of a black hole. And at least in that example, as you approach the black hole singularity, it's not true that you can see everything. So from outside, yeah, no. Well, the immediate answer is it appears to not be true, at least not, see, I can only discuss a collapsing universe from the point of view of somebody who lives in it. And that person, what that person can see doesn't grow as you approach the singularity. As your life is ending, you have a horizon, a past horizon, not a future horizon. So my first reaction to the question is no. Do I think we live in a black hole? Well, you see, part of general relativity is that we can't tell if we live in a black hole whose size is bigger than our horizon. We certainly don't live in a black hole whose size is smaller than our horizon. Are there any other questions?
Yes, maybe
May
I can
I
stop the
ask one?
recording. Oh, sorry, you can go ahead.
So the existence of the horizon and the singularity itself is make it harder to define the quantum theories in the. So if we somehow accept, as at least for geometrically, the white hole itself, and identify the horizon of the white hole and the horizon of the black hole, so that we have one complete space, so that we can define quantum theory on it. Do you think that is a logical thing to do, or
I think that
do we have a viable theory?
This is getting too detailed for me to respond to usefully now, I think. Let me urge you to consider it as a research question.
Okay.
I think it's getting almost. Let me just quickly look at questions in the chat, and maybe
Yeah, I think I can stop the recording and then we can have like 5 minutes more discussions off the record.
Okay, that's fine. If every state is local vacuum, can it be certain local measurements can't distinguish between vacuum and excited states? Well, certain measurements can't distinguish things, but yeah. Another question, should there be a formulation of black hole thermodynamics for apparent horizons? If you look in the contemporary literature, you'd find some things that are said that involve apparent horizons. I recommend a paper by Wall and Engelhardt from about 8 years ago. Okay. I think that's all the questions in the chat.
Yes.
So I think maybe, unless there's one very quick question from the audience, I think we'll call it a day.
Okay. If anyone has a question then. I guess not. Okay, well, thank you so much again for the great talk, Edward. It was a pleasure having you.
Well, thanks for the invitation and good luck to all of you. And as I said, hopefully
Thank you so much.
We'll go more deeply in the subject and contribute to unraveling some of the mysteries. In the
Thank you so
meantime,
much.
all best. Okay, thank you.